Okay guys, second video in Math 5500, and actually this is one of my favorite ones because it's yeah, we really get into kind of some cool stuff with R. And yeah, I don't know, I guess if I was going to title this video something, I would probably title it Everything I Would Want You to Have Learned in Undergraduate Statistics about Descriptive Statistics and Correlation and Regression. So if you know this stuff coming in, then the next 33 videos are going to be much easier on me. So what I want to again demonstrate, let's say that I sent a file, and let me open it up, and this file is called IQ Read. This is a really important video in terms of getting you started on R, where we can yeah, do some kind of simple stuff, and ultimately, guys, we get into some pretty not simple stuff. So we've got this Excel file, and it looks like it has something to do with reading scores and LSS, IQ. I think that's an estimated reading score, and we've got the gender, and we got the school district. So we want to get this file, which is now in XLS format, and we want to get this into R. Well, the first thing I'd want you to do is go up to File and go Save As. And I'd want you to name it something simple. So I'm just going to name it Read. I typically like for files like this to be all caps. I like them to be 3 or 4 letters with no spaces. Next thing I'm going to do is I'm going to choose a location where I want to save the file. So I'm always going to save it on my desktop. And the next thing I want you to do is I want you to come down and do a Save As, but I want you to do the format as .csv. That's comma separated values. I have found working a lot with R that getting a file in the format .csv into R is much easier, you know, really pretty seamless, if you will, than some of the other formats. All right, so again, we got that. We're going to save it. It's going to come up and make you feel like a complete idiot, like you've done something wrong. Just go continue. And then I'm going to go ahead and I'm going to close this down. I'm not going to save it because I've already saved it. And I'm going to shut Excel down. Now, if you look on your desktop, what I have, I have the file that I started out with, and that's usually going to be the format that I'm going to send to you. And then I have the format in .csv for the file called Read. Okay? Now what I got to do is I've got to go to R, and I'm going to open up R, and I need to get the .csv formatted file into R. Well, the very first thing I'm going to do, kind of where I ended off from video number 1, is I have to set the working directory. And my working directory is going to be users, ddarbro, and the desktop. I kind of wish I'd made a mistake there just to show you. Now, if this is all kind of new to you and you're wondering, oh, what goes first and is users capitalized and so on and so forth, you can do get working directory, and it'll tell you what your working directory was. You know, obviously mine's changed because I set it. But it'll tell you what your current working directory is and give you an idea of the you know, the form that you need to use to change your working directory. Okay, what I've done now is, what I've accomplished so far is with R, I now have told R where to go get the files I'm going to work with. So the next thing I want to do is I want to name my file something, or I name my data set something, and I'm just going to call it data. And now I'm going to use a command called read.csv. And remember, I think, is that right? Is that what I called it? Yeah, I did. And this is the reason I like to keep the file name something simple. I like to keep a file named with no spaces because, you know, one little slip up and it'll give you an error. Alright, I hit enter, nothing happens, that's good. When something bad happens, you're going to see the big red warning or error messages, which just aren't cool. Now I can type data, and I've got the data set imported into R. And as we saw last time, you would think that if I wanted to find, for example, the mean of READ, that I could go ahead and do that. Well, I can't. R sees data, the data set that I imported, but it's not ready to do any statistical calculations on it until I attach it. So guys, the first thing I've got to do before I run any statistics on this, do any mean, standard deviations, whatever it may be, is I have to attach my data. Now, if I want to go mean READ, if I want to find the average reading score for these 30 kids, then I can do that. Guys, you can't run any calculations until you attach your data set. Now, a lot of times in R, what I want to do is communicate to you. And if I use kind of a Twitterism, but if I use a hashtag, R now knows that I'm going to type stuff that is irrelevant to its code. I'm not trying to tell R to do anything. I am communicating to someone, in this case, namely you, because we're doing a screencasting. So I'm actually communicating. So I'm going to tell you now the goal for the next few steps is to, we're just going to just really just basic descriptive statistics. And notice I don't get an error. Now if I started communicating to you like this, and it gives me a plus, which is looking for more because it's looking for a command. Not cool. So I'm going to go second quit and get out of that. So actually I hit escape to get out of that. But notice when I started with hashtag, then I can communicate to you, and that's going to be important because you're going to do things on R that you're going to turn in to be graded, and there are going to be places where you're going to need to explain to me what you've done. So when you do that, you start with a hashtag, and don't start this or it gets into complete and utter madness. Okay, first of all, what I want you to come in from your undergraduate statistics knowing how to do is to how do we analyze so how do we perform basic descriptive statistics on quantitative data? Well, first thing we need to do is look at measures of center, which are the mean and the median. We also need to look at measures of spread, which are the the range, standard deviation, variance, quartiles. Let's just leave it with quartiles. Something else we'll want to be able to do is with basic descriptive statistics for quantitative data. We want to be able very quickly to take a look at a histogram and a box plot. Okay, so to find mean and median, very simple. And what I'm going to do here, I'm just going to focus, do all of these illustrations on IQ. So statistically, if I want to describe the 30 IQs for these kids in the sample, so I would do, well, mean IQ. So the mean IQ for these 30 kids is 111.2. Do the median IQ. The median is 111, so we have a mean and a median that are very close, which says we probably have a symmetric distribution. So speaking of, let's just go ahead and look at a histogram of IQ. Tell you, we're going to have problems. Now, why? Well, the reason we have problems is histogram is not the prompt to do a histogram. Actually, it turns out if we want a histogram, we have to use HIST. Now, when we do that, a second window kind of pops up, and we see that we have a histogram, and this gives us a, approximately bell-shaped and symmetric distribution as we would expect. considering that we're drawing from a population of IQ scores which are soon to be normally distributed. Now, threw a little curveball at you there, right here, on purpose. Sometimes what you're trying to find isn't intuitively clear. And if you go back to orientation, and I told you, some of the things that you can do to kind of help ensure success is to treat videos just like you would lectures. So guys, what I would expect you to be doing here, this is one of the simplest videos that we're going to have the entire semester. It's still going to be insane because I'm going to throw so many different prompts at you. It's going to be impossible for you to remember everything. So what I would recommend you doing is I would recommend you having a notebook for your video lectures from Math 5500, and in the very back, probably the last 5 pages, I would leave those just for language that we use in R. For example, I would make a note back there now that to be able to work with data, I must attach it. I would make a note back there that to bring a file that's in CSV format into R, then I have to perform this operation. So again, I would have the first part of my notebook, the theory. I would have the back part of the notebook specific to the language that we use in R. Okay? Guys, next thing I'd want you to be able to do is to find a box plot. And remember, a box plot gives us 2 things. It shows us the 5-number summary. It also gives us outliers. So we have a symmetric distribution here, and we have no outliers in this distribution. Hopefully, let me see if I can find something that does have outliers. Well, that one doesn't have outliers. What else we got going on here? Let's see if read does. Well, it doesn't either. Wow, this is just really good data. Well, looks like we're not going to have any outliers, but if there are outliers in a box plot, it'll be represented by an isolated point. Okay? Okay, measures of spread. The range is really easy to find. Now, it's not going to give you the range per se, but what it'll do is it'll give you the high score and the low score. Another way of doing that, if we have a large data set, is to use sort. And if we sort our data, it'll give it to us in ascending order from lowest to highest. So what this range does, it gives us 2 numbers. And at the end of the day, what it's giving us is the high and the low score. Now, some of us can do mental math. Some of us can't. And when the grade's really at stake, it's probably safe to do this. So the range of this data is 57, which is the difference between the high and the low. Next thing I would want to do is to report the standard deviation. So the prompt for standard deviation is just SD. The variance is 188.3724. Remember, the standard deviation squared is the variance, and the variance, the square root of the variance is the standard deviation. So if we wanted to verify that, which I don't really know why we would just kind of trust it, but if we wanted to verify that, we could take the square root of 188.37 this way and get the standard deviation. The next thing are the quartiles. Easiest way to do quartiles is just do the summary command. So the summary command will give us the low and the high in addition to the first and the third quartile. So what can we say from interpretations of this output right here? Well, the minimum IQ is 82. The maximum IQ is 139. The first quartile is 102, so approximately 25% of our IQs are below 102. Our third quartile is 117, so approximately 75% of our scores are at 117 or below. The IQR, which is the interquartile range, and this is not going to work. Oh, it did. Okay, I thought that was it. Okay, good. So the interquartile range is all caps. So the interquartile range would be 117 minus 102, which is 15. So the IQR 15 would say that the range of the middle 50% of our data is 15. Now, so what we've done so far for a quantitative variable, we've seen how to find measures of center, measures of spread, and how to find the two pictures that we'll look at the most, the histogram and the box plot. Now, how do we analyze categorical data? What if we want, for example, to evaluate gender or even school district? Clearly we've got categorical data, so it's not additive. So the things that we'd be interested in looking at there would be just, counts and relative frequency. And the charts that we use are pie charts and bar charts. So to describe categorical data, we'll find counts and, well, we typically call them frequencies. And the pictures are pie charts and bar charts. Guys, don't y'all wish it stayed this easy? It's not going to, but enjoy it while it lasts, all right? To take a look at, let's just look at gender. What I would do there is I would use the table function, and that works out really cool. So of the 30 participants in this data set, we have 12 females and 18 males. Now, if we wanted to do a relative frequency, we would do something like this. The first thing that, one of the first things I do, at least, is to find the sample size. And to find the sample size, we would just do length of whatever variable, and I'll tell you what, let's keep it consistent here. Let's do length of gender. And, we have a balanced data set here, so the length of all the variables is the same. And, we have no missing data, so we don't have to be concerned with that. So sometimes I go ahead and identify the sample size as n. Now, to get the relative distribution, and I'm just going to call it this. So you probably see an emerging theme here, right? What I start out with, this is a name. This is telling me to perform an operation and name it this. So what I want to be able to do here is I want to take the counts, which I can get from table, but I want to divide this by n, and then I want to multiply by 100. Now, good. No red error or anything, right? So now if I type relative distribution, you can see that 40% of the participants are female and 60% are male. Now, you could have easily divided by 12 by 30 and 18 by 30 and got the same thing. But guys, this is a very, very, very simple data set. Some of the data that we'll be working with will have over 1,000, a sample size over 1,000. And you'll have far more than just one or two categories in in the categorical variables. So, just getting you prepared for the stuff that we have coming ahead. Okay. Now, another thing that we could do is we could use the table function to look at gender across school district. And what this will do, it'll give us counts, of gender across the 4 school districts. So, if I'm looking at this, if I'm conducting a study on this, and something that really matters, I may be slightly concerned that in school district 1, the proportion of males to females is nowhere in line with the proportion of males to females. Well, actually. Yeah, there's some stuff that I would be concerned with there. Let's just file that under to be learned later, okay? But there's some stuff there that I would be slightly concerned with if if I really cared about this data set, it's something that I was using for something other than just a simple illustration. Guys, something else that we may want to do is we may want to combine quantitative I swear I can spell, I just can't type. Combine quantitative data and categorical data. For example, it may be nice to be able to look at a pie chart. I'm sorry, to be able to look at a box plot of IQ scores across gender. And what this command allows me to do, let me get this out of the way here. And again, let me back up a little bit. This is the beauty of having lectures recorded. If I go too fast, hey, you know what? You can slow me down. All you have to do is just hit pause, and do what you need to do, and then hit play. And you know what? Guess what? I'll be right here waiting on you. So when we look at the side-by-side box plots, we can see that the mean IQ for males is slightly higher. The value for Q3 is slightly higher. There's more variation in the male scores, and when divided out, we actually have a female that's classified as an outlier, which has an IQ, quite low. It probably, I think it was about 82 is what we had. Okay, let's move into correlation and regression. This is kind of the kind of stuff that I would hope that you come into the class knowing. If you don't know this, don't flip out on me. It's fine. We'll get you caught up. But this is the kind of stuff that I would really like if you already know from your undergraduate statistics courses. How do we talk about correlation and regression? The first thing, correlation, what I want you to think about here is this is just a method for describing the relationship between two quantitative variables. Correlation has three parts. First of all, we'll want to be able to take a picture, and we call that a scatter plot. The other is a correlation coefficient, and the other is the coefficient of determination. Guys, this is the coefficient, correlation coefficient is R, and the coefficient of determination is R squared. So let me show you how to do this, and let's just assume that our goal is to examine the relationship between IQ as a predictor of I think there was a reading score, is that right? What we call that? Yeah, read. So we want to see if there's any relationship between a kid's IQ and their reading score. And again, we're going to keep it simple here. We're just going to do so in terms of a descriptive manner. We're not taking these 30 kids and generalizing to any larger population. We're not conducting any inference. Trust me, that'll come soon enough. Right now, we just want to keep it simple and look at the examine the relationship between the two. So guys, first thing I'd want to do is a scatter plot. So I would do plot, and there's two ways to do this. The first thing we can do, if we just want to use, x comma y, this works fine, and I'll show you how this works. So when we examine, IQ and read, and notice whatever variable that we put first, in this case IQ, will be our predictor, and read will be what we're trying to explain. And there's a slightly positive relationship here, but you know, there doesn't seem to be much of a linear tendency in terms of the two. Okay. Now another way we can do this, and this I'm going to show you this because it actually plays a role later in the class, if we use plot read tilde IQ. Now this is just a different format where whatever we put first is our y and whatever we put second is our x. And this could be a common form when we get into linear models and general linear models later on in the class. So we flip the two. If we use a comma, what comes first is our x. If we use a tilde, what comes first is our y. So guys, either one of those are going to work just fine in this class. Next thing we want to do is look at the correlation between IQ and read. So the correlation coefficient here would be R. So I may store this as R, and then from here on out, if I hit R, I have a correlation of 0.52. The guys, at 0.52 indicates that we have a moderate and positive relationship between IQ and read. The break-off correlation coefficients have to be between -1 and +1. The breaking point, and this is not cast in stone, but it's kind of a good rule of thumb. If we have an R value between 0.8 and 1, we have consider that to be a strong relationship, a strong positive. If we have an R between 0.2 and 0.8, we call that a moderate. And 0 to 0.2 would be a weak positive relationship. Same thing on the negative side, from -0.8 to -1, strong negative. -0.2 to -0.8, moderate negative, and 0 to -0.2 is a weak negative. If we want our R squared, the easiest way here would, I'm going to call it something. So let's go R squared. And guys, this is just literally my R value squared. So R squared is going to be 20.2757. R squared is reported, is always reported as a percentage. So our R squared is 27.6%. Now, what does this tell us? This tells us that 27.6% of the variance in Y, which is our read, can be explained by the regression on X, which is IQ. So 27.6% of the variance in Y can be explained by the regression on X. Now, we look at this in a simple form at first, and our ultimate goal, we get into multiple regression, logistic regression, so we'll eventually get into the variations on the predictors in X. We'll have sets of predictors, and but again, that's all to be learned later. Okay. Next thing we want to do is the second part is regression, which has the goal of predicting Y from X. And it turns out in R, this is very easy to do, and I usually just call this my model. And the command is just LM, and our Y value here is read tilde IQ. So this is a situation where we need to use the tilde, and we start out with the Y as a function of X. It gives us some kind of cool stuff. Not really. Actually, it just gives us the intercept and the slope. But nevertheless, what we know here is that from this model we can predict a kid's IQ by taking negative 39.62 plus 0.89 times the kids. Guys, that's not right. It's the great thing about class is when I do bozo stuff, students can stop me. So we're predicting Y. So we can predict a kid's reading score from their IQ score using the following model. So a kid with IQ equal to 115 will have a predicted read of whatever that turns out to be. Okay, I think what I can do, actually, I think I can just copy that and just paste it right here without the, nah, not going to let me. So I'll tell you what, let's just go ahead and, I'm pretty sure last year when I taught this class, I didn't go into the kind of the basics as much at first. All right, what's going on here, boys and girls? For some reason, it doesn't like that negative 39.62 first. Okay, I see what's going on. It's going to force me to use multiplication. Wow, picky. So take 102.35 and subtract 39.62. So the predicted reading score would be, about 63. Okay. Now, we're going to take this and run with it in all kinds of crazy places eventually. But one of the first things that we'd want to do after getting our linear model is calculate the residuals. And guys, in bigger, broader terms, the residuals are just the error in our model. Formal definition of a residual is residual is equal to our observed Y minus our predicted Y. Okay? Now, residuals are really easy to get once you run your model. And the command for this is just RESID. And again, we have our model. And, we have our residuals that are just very quickly calculated. If we want to come in, we can get what's called our fitted values. And our fitted values are just the predicted values. So if we put the first value in our model, what would be the predicted value? The residual is just the difference between the observed and the predicted. Now, I think this comes in a lot easier if I'll use something called a data frame. And let me show you how this works. If I come in with data frame, which is data period frame, and let's combine the madness. Okay? So first of all, I'd like to have my X first. In this case, this was IQ. I'd like to have my Y second. So in other words, I'm taking my data set that I started with, but I want to eliminate a bunch of stuff that doesn't apply and just get the stuff that does apply. I'd like my fitted values to come in next, and then I'll be able to be able to look at the residuals like this. So if I do that, it's kind of cool because it restricts just what I want to look at. So guys, let's think it through. The first child, and I know a little bit about this data set. I know these are kids, and has an IQ of 133 and a reading score of 94. Now, how did they get this fitted? Well, they use our model, which was the x value 133 times our slope, and I'm going to have to go back and get this. That was what, 0.89? And then subtract the intercept, which was 39.62. And if we do that, we get 78.75. Now, why is that different? Well, that's different because we rounded to 2 places. This kind of stuff drives my students absolutely crazy. I don't think it's going to be an issue here, but let's go ahead and run it out to 0.8923. And I'm going to, again, I don't think I completed my thought a while ago. I'm going into more detail with you guys because one of the things that, from the feedback from the first students I taught in this class, is that they didn't feel that we got a really thorough understanding of the basics before we got into the hard stuff. So if this is boring you to death, then you know what, good for you. But I'm pretty sure there are probably some people in our class that can benefit from this. That was 39.62, yeah. So when we put everything in, you get 79.0533, and you can see we're still a little bit off. But we have a better, higher degree of accuracy because, we used our slope and our intercept to more digits. Now, the residual would be the difference between the observed and the predicted. So the observed read is 94, and the predicted is 79.0533, which gives us our 14.95, which is exactly what we get as our residuals. Now, the purpose of residuals, the purpose of examining the errors is to determine if a linear model is appropriate for describing the relationship between, let's just go generically, x and y. And what we do here, for now, and I'm gonna complicate this as we go along, but for now let's keep it simpler. What we want to do is we want to examine the scatter plot of our residuals as y over our IQs, which are x. Now, if we have a random scatter plot of our residuals over x, this indicates that a linear model is appropriate. If we get into what's called a U-shaped scatter plot, this indicates that a linear model is not appropriate. And guys, again, we're going to get into fanning out of our residual scatter plot. We're going to get into a lot more as we get into more sophisticated measures. But let's crawl before we start running sprints here, okay? So what I want to do is do a scatter plot. So I have my residuals as, did I save those as RESID? No, okay. So I need my residuals for my model, tilde over IQ. And what I get is I get, again, my residuals mapped over IQ. And you can see that we don't have a U shape, so it appears that a linear model is appropriate for describing the relationship between IQ and read. All right? So guys, that's about all I got for you now, which is kind of cool. On to probably the next couple of videos, we'll again get into statistics background. I want to get into some ANOVA, possibly even some two-way ANOVA, because they play important roles in the future of this class. So, guys, have a good one. That's it.